Well, thanks for inviting me. Heard a lot about SAR today, but now we're going to be in more in the LiDAR realm. So I'm going to do a little bit of Optech overview. That's something you have to bear with me on. I have to say something about the company. But then I'll talk about a few of our ALTM systems, our seasonal system, and then talk about some data fusion at the end. So a few slides here on Optech. We've just celebrated our 40th anniversary a month ago. So some of the marketing stuff here. LiDAR is basically our core technology, time of flight. Airborne bathymetry is what I'll be talking to you about mostly. But we have mobile systems and static systems. So pictures of some of the instruments. The LiDARs, the bathymeters, cameras. We do some custom LiDARs, and this is one that we're particularly proud of because we're a key partner in getting a LiDAR on Mars. And the big news story that year was that it was a Canadian group that found snow there, so that was very appropriate. And here we have our mobile mapper. Well, here's a way of combining marketing with science. We started a while ago, as you can see, and our first serious airborne bathymeter was delivered to the Canadian Hydrographic Service because Larson was a Canadian Arctic explorer, but it was a whopping 20 hertz, 20 times a second. But you can see the log graph here and how we've advanced. We got to a kilohertz and 3 kilohertz as part of the Shoals generations of airborne bathymeters. Seasonal went to 10 kilohertz. The Aquarius, I'll show you, is now at 70, and we're going even higher. So first of all, we'll talk about the Aquarius system. Just a brief slide here of where the market niche is for airborne bathymeters. As you use multi-beams, the sonar systems, their swath is totally dependent upon their depth. And of course, in the shallow waters, it's not only inefficient for them to go into close to shore, but it's actually dangerous. So being able to fly at a constant altitude and a constant swath gives you good survey coverage, and it's a lot safer. So it's in the shallow coastal waters that the airborne bathymeters excel. The basic principle is that we send down a green laser and an infrared, actually. The infrared finds the surface of the water. The green finds the bottom. We digitize it, and we do the time of flight. We change for the speed of light. We change for the Snell's law of refraction, and we get the elevation and position on the sea bottom. So the Aquarius system was based on the ALTM Gemini, which is very similar to the 3100 that is in the Neon system. We basically took this infrared sensor head, it's at 1 micron basically, the laser, and we changed the laser to make it green. So it's a true green Gemini. It's very similar then, it's got a similar scan width. The scanner can go from 0 to 70 hertz very quickly across each way. We capture up to 4 range measurements on the discrete side, and we can go up to, as I mentioned before, 70 kilohertz with the green system. So 70,000 times a second. For all of our systems, we do extensive ground truthing to calibrate them. Mostly the terrain mappers are calibrated over local runways, so it's the Oshawa runway just east of Toronto, in Peterborough, Ontario. For the bathymeters, we also had some sonar collected for the sea floor, well, I shouldn't say sea, for the Lake Ontario floor, that we use extensively for calibrating those instruments. So here's some data from Aquarius. This is the Scarborough Bluffs, for anyone familiar with Toronto. It's quite a vertical drop here, east of Toronto. The light blue or green is the water surface, and the blue is the Lake Ontario lake bottom. So you can see that we had some areas where the bottom was not detected. Of course, what you get back is heavily influenced by the reflectivity of the bottom. If it's black mud, not many photons come back, so that's a challenge. But you see we did get to about 12-meter depth in Lake Ontario with this instrument. I should note that this was using only the discrete electronics. Just as the terrain mappers don't need a digitizer, you could also use this without a digitizer and just use the CF constant fraction discriminators or electronics to get the timing of the pulses in the returns. Just a quick shot of our software. We designed a custom software to derive the bottom timing to get the true depth elevations. A key factor in this system is to separate the land from the water, and that's something that we're still working on. We have, I guess, semi-manual methods where you could draw a shape file as an input, or you could use a mean water elevation to distinguish between the land and water elevations. So here with the discrete electronics, this is the water surface, and this is the bottom. And what's of note here is that you have this gap here close to shore. And that's because the discrete electronics is limited in its pulse pair separation. If two pulses come together, it will not be able to distinguish them much before, in this system, about 1.5 meters. Some of our laser mappers can get well below a meter in pulse pair separation, but that's still a limitation here for the very shallow water, and when you're under a meter of depth. So you do require waveforms to go even further to fill in that gap. And here's a case where we digitized the waveforms and analyzed them. A little bit difficult to see, but you can see there's a seamless transition from land to water, and that's shown more clearly in this profile here. So that's where the digitizing of the waveforms really helps a lot. This is the intensity of the LiDAR. It's a very good way to distinguish between land and water. You do sometimes, I mean, I've heard a lot about speckle today. Well, this is, I guess this is speckle from the water surface coming back to our LiDAR. So you do get some high intensity returns, but you can see if you ran a filter based on density or spatially, there would be not much question of where the land and the water were. On the left is just the elevation, the color-coded elevation. And of course, as a LiDAR, it's not just a bottom mapper, but it can do the terrain as well. So it's just an example over a suburban area of the Aquarius data. I don't think I mentioned, the Aquarius only puts out the green wavelength at 532 nanometers, actually. So this is elevations with a green beam. One limitation we do have is due to eye safety. The green beam is 4 times as unsafe as the IR, and so because of that, our green spot by the time it hits the ground must be of the order of 70 to 100 centimeters. With the infrared beams, we can make them much tighter, down to 15 or 20 centimeters, which helps a lot in your spatial resolution of objects and of buildings. But the green beam does have to be larger for eye safety reasons. So the applications for the Aquarius, I guess they're kind of intuitive. Basically, be able to get that shallow water as well as the terrain really can make a big difference for some surveys. It's limited to about 10 meters of clear water, the Aquarius system. It's not a deep water bathymeter. I'll talk about another one later, but it's a good shallow water mapper. And basically, you can go down to 10 plus meters in relatively clear water. We sold the first Aquarius to the University of Houston, the National Center for Airborne Laser Mapping. Just want to show you a few results there. They took it down to a very nice location down in Destin, Florida. Here in the Panhandle, this is the area they surveyed. Nice bright sand, looks like. And from a flying altitude of 500 meters, they were able to get down to 12 meters or more. They also did basically some seagrass mapping underneath by basically looking at the roughness of the returns from the sea bottom, and they were able to correlate that with some seagrass. A more recent survey was done in Italy. At the top here, there was just a couple of flight lines along the shore. This one is colored by classification. We can classify land in green, the bottom is blue, and this one is just colored by elevation. This shows the big difference between the, you do have to correct for the speed of light. Basically, if you don't correct for the speed of light, you get the bottom yellow curve. But of course, light speed slows down in water, so the true elevation is given by this green curve. And you see we got, in this case, we saw deep water here, but there's something going on here, and it could be that it's the reflectivity issue, basically, of what's on the bottom. Just another example from Italy. There's a very sharp drop-off around this island. Again, land and water classified here, and then this is elevations. So down to almost 14 meters, but it fell off quite quickly around this island. Okay, another system that we're developing actually, and that's to add another wavelength. We already have a Pegasus is one of our terrain mappers. It can collect up to 500,000 shots a second with a dual beam configuration. Well, we thought, what if we add another beam? So we're working on it now. Most of our terrain mappers are at 1 micron, 1064 nanometers. You can double that to get your green, the 532 and a neodymium YAG or YILF laser. So we're going to have these two wavelengths, and we're adding a 1.5 micron to this system. So it's going to be 3 beams. So the 1 micron will be about nadir, 1.5 at 3.5, and the green at 7. And it was done on in this way on purpose, because having the green beam at about 7 degrees off nadir is more beneficial for the bathymetry, basically. And you do want to avoid those specular nadir returns. That's a very similar analog as we've heard earlier today. And we're quite confident we'll get up to a 2-kilometer altitude with all 3 wavelengths. So they'll be collecting all 3 wavelengths at the same time with the following scan pattern, basically. They'll be designed to sweep across the aircraft as we fly with just about half a meter spot spacing. Of course, that depends on your altitude and your flight speed and so on, but that's a typical number one could get. So, yeah, the 7 degrees I've mentioned. We think this will have an even better performance than the Aquarius, down to 15 meters in decent water. And we think it has great potential for using for terrain classification, basically. And we've have a fair experience in that in our Optech Mississippi office, which I'll mention in a second. And of course, the bio or carbon mapping application is definitely of interest. If those 3 wavelengths, or even another wavelength, because we're basically using fiber lasers in these systems. If there's another good fiber laser of another wavelength of interest, then that wouldn't be too hard to put inside. So let me switch now to a true airborne bathymeter, not a much deeper water mapper, and that's the Coastal Zone Mapping and Imaging LiDAR, or SEASMIL. It's a much larger system, but it has to be in order to penetrate as deep as possible. The Shoals generation of systems only had a 10 centimeter aperture, and it was good down to maybe 30 meters or so, 30 or 40 meters. The SEASMIL, we've come up with a design to double that aperture, which is 4 times the collecting efficiency, and it was designed specifically to look through even deeper, muddier or more turbid waters, because the U.S. Army Corps really wanted to look at their harbors and channels, and some of those are not so cooperative for clear water conditions. So here's some examples from We've built 5 of them now. Had surveys in Hawaii, Mississippi, of course, where it is built down in the Kiln, Mississippi office. Demo was done in Korea. And a very special software processing package was developed called HydroFusion. We combined the Shoals LiDAR with hyperspectral back in 2005 and onward, but the customer had to use 7 or 8 different software packages to combine all the data products and then data, and then to get the products they wanted, they literally had to use 7 or 8 packages off the shelf. Well, HydroFusion was designed to just have one window where they could derive all their products of interest. I'll just show you those here. So these are the different products that we can get from the LiDAR and from the hyperspectral camera. It's a Cassie 1500 made by ITRIS here in Alberta. So the LiDAR depth, of course, we can get an indication. If you remember the backscatter curve I showed you of the water, by analyzing that you can get an idea of basically the attenuation of the water itself, the water volume from the LiDAR. We can get a relative reflectance of the seafloor by looking at the intensity of the return from the bottom, because we know what the bottom amplitude is. From the Cassie, we can get the surface reflectance of the water. And then going deeper, we can get some idea of the chlorophyll concentration, CDOM, or the organic matter of the water volume, the backscattering particles, the hyperspectral C4 reflectance. But then I guess the holy grail that this whole program was interested in was a true classification map using the LiDAR and the hyperspectral to come up with classifying the sea floor, where this is off the coast of Florida, Fort Lauderdale. So it's there's coral here, sand, vegetation, and so on. So they've been very successful in combining all this in one package to get this classifications and all these data products. An example from Lake Michigan. I mentioned before that we specifically designed the system to really go through turbid water and not bright sand from Florida, but more muddy bottoms. And so this is a case where this is the results they got from just their normal algorithm. So this is a channel here you can see in the surrounding. This is the width of each flight line. So you see there's many flight lines going over this area. Well, they came up with this turbid water algorithm, and that's the result, how it fills in, basically. So they really pushed the algorithm to examine the waveform and to derive the bottoms from very weak returns. So that was the U.S. Army Corps of Engineers was very happy with this because, as I said, most of their focus is on harbors and so on. Well, we've won a few awards. I guess more marketing to end, but won a few awards. The Aquarius was an innovation back when it was made, and then the Seasmills won a few itself.